Hi everyone, in this video I'm going to talk about experiment 9, the nucleophilic substitution reaction. And this reaction involves a very theoretical, uh, you know, difference between SN1 and SN2 reactions, and basically you're going to actually analyze experimentally or empirically what happens. Why are these reactions different? The reason I point this out right at the beginning is because this video will be a little different than the other videos where I kind of talk about the experiment a lot and then talk about the theory after we have a good perspective on what's going on in the experiment. Here, it seems to me to make more sense to talk a little bit more about the theory, and the experimental will kind of come out during the theory, and then maybe seeing how it goes, I'll briefly reiterate the experimental part. But the experimental part here is, it's a few paragraphs, and it's pretty straightforward. So, although there are some key safety concerns. So, without going into too much more detail, let's get right into it. So, you're actually going to do two reactions here. The first reaction you're going to do involves 1-butanol. And the second reaction you're going to do involves T-butanol. So these are isomers. These are isomers, and they only differ in the arrangement of the carbons. So you both have 4 carbon chains. Well, in this case it's a chain, but here you have 1, 2, 3, 4 carbons, and it's kind of like a little ball, if you will. So these are the two molecules we're going to use. Then we're going to add a mixture of ammonium chloride, ammonium bromide, and sulfuric acid. And we're going to do the exact same thing in both cases. So we're going to add ammonium chloride, ammonium bromide, and sulfuric acid. Whoops, sulfuric acid. So one thing to note is this should be alarming to you. Adding chloride and bromide salts in sulfuric acid seems like a terrible idea. Why? You're going to protonate H, you're going to protonate Br, make HCl and HBr. HCl and HBr are gases. So remember that when you're doing this, you have to do it carefully. And I'll explain how to do it carefully later. Just briefly, what you're basically going to do is add the concentrated sulfuric acid to ice. This has two effects. It dilutes it and it cools it down. And then the diluted cold sulfuric acid mixture in the hood can be added to these compounds. If you add straight concentrated sulfuric acid to these compounds outside on the bench, you will not be having a good time, because you will make hydrochloric acid and you will make hydrobromic acid, which are both gases, and will go into the gas phase. You breathe in the gas phase, so don't do that. Make sure you add this to ice first, and then in the hood, add them together. Anyway, now that we've talked about the safety concerns, which of course are extremely important, which is why I'm going to mention them a couple times, what we need to do is look at the difference. Well, this is a nucleophilic substitution reaction. So we're going to substitute the OH with a Cl and a Br. And we're going to use a mixture of these two compounds in a 1-to-1 stoichiometric ratio. And that is true for both this reaction and for this reaction. And in the top case, we're going to get some of this and some of this, and water as our byproduct. So we've just substituted the OH with Cl and Br. It's a nucleophilic substitution reaction. And in the bottom case, believe it or not, we're actually going to get the same thing. We're going to substitute some of this, and we're going to substitute some of this, and we're going to get water. So we're again going to get the chloro and the bromide substitution, because we've added a 1-to-1 stoichiometric mixture of the chloro and the bromo. Notice that the 1-to-1 stoichiometric mixture is not the same mass of these compounds, okay, because they have different molar masses. So it's not the same mass, but it is the same number of moles. So at this point, you're probably asking yourself, okay, this doesn't seem interesting. You've just done the same thing twice. Well, that's where this reaction gets very interesting, because we have not done the same thing twice. Because although overall we have substituted chlorine and bromine for OH in both cases, these reactions are not proceeding in the same way, which leads me directly to the mechanism. So let's look at the mechanism of this 1-butanol. In the presence of NH4Cl, NH4Br, 1-to-1 again, and sulfuric acid. So the first thing to note is that Cl and Br can't simply do a nucleophilic substitution on OH. They can't replace OH. Why? Two reasons basically that are the same reason. OH is a strong base, or said another way, OH is a bad leaving group. So OH isn't just going to leave for a Cl or a Br. So what can we do to make OH a better leaving group or a weaker base? Well, that's where the sulfuric acid comes in. So I talked about the safety concerns earlier. Never add sulfuric acid directly to chloride and bromine salts. You have to dilute it first, and in our case, we dilute it in ice to also cool it down. Furthermore, we work in the hood. But what sulfuric acid does is it's a source of protons. So what happens is this molecule attaches there. And what we end up with is OH2 and a positive charge. Now, water is a weak base and a good leaving group. So this molecule can leave. In this case, the OH acts as a nucleophile and attacks the H, or the H acts as an electrophile and is added to the OH. So it's important when you're doing your mechanism discussion that in each step you identify the nucleophile and the electrophile. Now, furthermore, we have a good leaving group. However, if this were just to leave, we would end up with a primary carbocation. And primary carbocations aren't very stable. So what has to happen is X minus, which is either Br minus or Cl minus, has to come in, and what we end up with is this transition state where we have the X minus coming in and the OH2 plus going out. So this transition state occurs. And then finally, what we end up with is some Cl product, some Br product, and water as the byproduct. What is interesting about this? Well, what is interesting about this is that this is an SN2 type reaction. Why is it an SN2 reaction? Well, because it has the transition state. Or, said another way, from a physical chemistry standpoint, the rate law equals K, concentration of the protonated alcohol, and the concentration of X minus. So the rate of the reaction depends on the strength of the nucleophile, because the nucleophile is in the rate law. It turns out that bromide is a better nucleophile than chloride. So the rate of bromination will be greater than the rate of chlorination, because bromine is bigger and it's less solvated. Another way of saying that is it interacts less strongly with water. So the bromide can kick out the OH2 faster than the chloride. So if you use this as the limiting reagent and you have an equimolar mixture of this and the bromide reaction happens faster, you're going to end up with more of the bromo product and less of the chloro product. Well, how are we actually going to monitor that? Well, the way we're going to monitor that, and this obviously has nothing to do with the mechanism, is by GC. And I'm not going to talk extensively about GC here, but GC is a separation mixture that separates molecules based on their boiling point. So when you do this, you're actually going to use pentane as the solvent. So what you should see in your GC, so this is kind of the peak height, which we use picoamps, and this is time down here. So what you're going to see is first you have pentane, just a 5-carbon chain. This is just your solvent that you're going to use in your liquid-liquid extraction. So what you first see is a very large peak for pentane. Now, the staff may or may not have cut this off. Sometimes we start the profile that we actually print out after the solvent peak comes out. And the reason for that is because it's much bigger than the other peaks and it makes it easier to see the other peaks. Then, what's going to come out next? The chloro product or the bromo product? Well, GC separates compounds based on their boiling point. And I talk about this more extensively in another video, which I will try to link to below. And basically, what we're going to do is we're going to separate them based on their boiling points. Well, these are the same molecule, essentially, except the only difference is the chlorine and the bromine. Well, chlorine has weaker dispersion forces, and therefore chlorobutane, 1-chlorobutane, has a lower boiling point. So it should come out next. And there should be less of it. So we see a small peak for the chloro. Please do not go based on these relative peaks and expect to see these. I'm making this up just as an illustrative example. The relative nature is correct, but the absolute nature is not. Then we're going to see the bromo peak come out last. And the bromo peak should be bigger than the chloro peak. Why? Because bromide is a better nucleophile in aqueous acidic media because it's less solvated. It's interacting less strongly with water. So this is the mechanism of the SN2 reaction. Again, we're comparing the SN2 reaction to what's ultimately going to be the SN1 reaction up here because at first glance they look the same until we consider the mechanism. Now let's look at the other one. All right, in this case, we have T-butanol. And we have it in the presence of NH4, Cl, NH4, Br, and H2SO4. Again, we have the alcohol, not OH of the alcohol, not being a good leaving group. So the first thing is protonation. So the OH acts as a nucleophile and takes the H+, and what we end up with is the protonated alcohol with a positive charge like this. Now this time, when this leaves, we form a tertiary carbocation. And tertiary carbocations are relatively stable. So we can actually have this occur. Whoops, I messed that up. We end up with this tertiary carbocation like this. Now, once we've formed the carbocation, we have X minus. So X minus acts as the nucleophile and comes in and attaches. In this case, the water was kicked out in this step. And we end up with, because X minus is a mixture of chloride and bromide. So we have nucleophile in solution. You can see them here. Okay, these come in and they overtake this. Well, what is the rate of this equation? The rate here is equal to K concentration of the protonated alcohol. Because the rate, the slow step, is the formation of the carbocation. Once the carbocation is formed, it pretty much reacts instantly with the first nucleophile it bumps into, because this is relatively unstable and it wants electrons, and nucleophiles have electrons. In this case, Cl- and Br- have electrons. Notice what's not in the rate equation in this one is the X minus. So this is an SN1 reaction. Note that the 2 is because the rate depends on two things, and the 1 is because the rate depends on one thing. So since the rate only depends on this, it doesn't depend on the concentration of the nucleophile. Said another way, if we start with a 1-to-1 mixture of this, we should end up with a 1-to-1 mixture of these, because this is going to react with the first nucleophile it bumps into. And if there's an equal molar mixture of these, it's got a 50-50 chance, an equal chance, of hitting either nucleophile. Let's look at the GC of this one. So here we have picoamps, and here we have time again. We're again going to have a large pentane peak, which you may or may not see in your spectrum, depending on how we have it set up. But this time, the chloro product's still going to come first. These are still the same molecule, only differing by chloro and bromo. So chlorine has weaker dispersion forces, so therefore, because it's smaller molecule, smaller atom, so therefore it is going to have a lower boiling point. The bromo bigger and higher boiling point. But this time, we should see equal peaks. So this is our pentane. This is our chloro product, and this is our bromo product. In the previous case, this was our pentane, this was our chloro product, and this was our bromo product. The difference between these reactions, which if you recall, look fundamentally the same at the beginning, is that this reaction occurs by an SN2 mechanism, and this reaction occurs by an SN1 mechanism. Therefore, when we look at the two GCs, for the the SN2 reaction, we expect to see less chloro product because chlorine is a weaker nucleophile in an aqueous acidic media. In the case of the SN1 reaction, we expect to see an equal amount of the chloro and bromo product because the rate does not depend on the nucleophile. So therefore, if you start with a 1-to-1 mixture, you should end up with a 1-to-1 mixture. So that they look the same at the beginning, they ultimately are not the same at the end. So now that we've talked about the theory of the reaction, which I think is extremely important here, let's talk a little bit about the practical aspects. So the first thing you're going to do is you're going to prepare this nucleophilic medium. And you're actually going to prepare one big batch, if you will, and then break it into 2 equal portions, and you're going to use half of it for the SN2 reaction and half of it for the SN1 reaction. So to prepare this nucleophilic medium, the first thing you're going to do is you're going to take your sulfuric acid. You're going to use 10 milliliters of concentrated sulfuric acid, and you're going to add it to 30 grams of ice. This is very important because this dilutes the acid. It also cools the acid down. You do not want to add warm concentrated sulfuric acid to a mixture of chloride and bromide because, again, it will make hydrochloric and hydrobromic acid. You especially don't want to do this outside the hood because then you will breathe in that hydrochloric and hydrobromic acid, which is dangerous. So don't do it. All right. So make sure you first dilute this by adding it to 30 grams of ice, about 10 milliliters of it to 30 grams of ice. Then you're going to use 3.8 grams of the ammonium chloride and 7 grams of the ammonium bromide, which is an equal molar mixture. Note you don't use the same masses because they have different molar masses. And you're basically going to put this into the flask and dissolve these things to make the nucleophilic media. You're going to have 40 to 50 milliliters complete of nucleophilic media because you have 30 grams of ice, 10 milliliters of concentrated sulfuric acid, and then about 10 grams of salts. And overall, you're going to have somewhere around 50 milliliters, of solution. You're going to use half of that solution to do the SN2 reaction and half of that solution to do the SN1 reaction. Now, for the SN1 reaction, for the SN2 reaction, we actually need to heat up the reaction mixture. And I want to show you a picture. So basically, what we're going to do is add about half of the nucleophilic mixture to the round bottom flask. Then we're going to set up this gas trap apparatus, which looks like this. So you're going to have a condenser with water in and water out. But instead of just having this open to the air, you're actually going to run it through a gas trap so that if any hydrochloric or hydrobromic acid is formed, it'll get trapped here and it won't go into your breathing space. And here's a picture of it, like a diagram of it, and here's what it looks like in real life. So make sure you have this gas trap hooked up before you start your reaction. What's going to happen is any gas that comes out of here is going to bubble through water, and that should dissolve hydrochloric and hydrobromic acid. So if it dissolves in the water, that's a lot better than you breathing it in. So make sure you have this all set up. Once you have this all set up and you have your nucleophilic mixture here, before you start heating it, you're going to add 4 milliliters of the 1-butanol in order to get the reaction to go. You're then going to reflux the mixture for about 45 minutes and then cool it down and work it up. After we talk about the T-butanol, the SN1 reaction, we'll talk about the workup in form of a separation scheme. So while this reaction is refluxing for 45 minutes, and plus you have a lab partner, so you can break up the work, okay, you're going to want to prepare the SN1 reaction. It turns out that this reaction goes easier than the other reaction. So in the SN2 reaction, we added about half of the nucleophilic media. Not surprisingly, we're going to use the other half of the nucleophilic media for the SN1 reaction. But this time, you're going to put it in on a round bottom flask, but you don't need to set up the reflux apparatus. So you're only using this apparatus for the 1-butanol. You're not using it for the T-butanol T-butanol being this one, okay? Not for the 1-butanol. So, sorry, you are using it for the 1-butanol, not for the T-butanol. For the T-butanol, you simply just set it into a round bottom flask on a stir plate, gently stir it, and add 4 milliliters of the 2-methyl 1-propanol, which is T-butanol, to the flask, and you can just put a stopper on it and allow it to stir for several minutes. It's very important that you do not heat this up. It doesn't have a condenser. It doesn't have a gas trap apparatus, so you're just going to do this at room temperature and stir it for 5 or 10 minutes and it'll go. This reaction goes easier than this reaction, so this one requires heat, this one doesn't. It's very important you do not heat up that closed flask because that's extremely dangerous. All right, so now that I've rambled awkwardly through the experimental procedure, which again you can just read, it's only a few paragraphs, I'm kind of reading it as I tell you it, so that's why it's so awkward. But anyway, let's talk about how we're going to work up this reaction mixture. And we're going to talk about how we're going to work up the reaction mixture in terms of a separation scheme. So we're going to do a separation scheme at the exact same time as we do our discussion. So the first thing to notice is that separation schemes start at the end of a reaction. So when the reaction's over, the separation scheme begins. I always give the example of aspirin. Aspirin is made with salicylic acid and acetic anhydride in the presence of sulfuric acid. Nobody wants sulfuric acid in their aspirin. You probably don't want salicylic acid or acetic anhydride either, but you definitely don't want sulfuric acid. So we have to separate the aspirin from the stuff required to make the aspirin. It's just something chemists do, and in this course, something you do. So what we're going to start with is the products. 1-chloro butane and 1-bromo butane. So I'm looking at the SN2 reaction. I'll be honest with you, the SN1 reaction is exactly the same, except it's T-chloro and T-bromo. The next question is there any 1-butanol left? I do not know the answer to that question. Okay, there may or may not be 1-butanol. So you could put trace 1-butanol on the separation scheme, or you can skip trace 1-butanol on the separation scheme. The argument for 1-butanol is that the chances are the reaction doesn't go 100% to completion. The arguments against it is it's the limiting reagent, so there isn't going to be very much of it left. Use your judgment. It doesn't really matter. There's no right or wrong answer here. It's more of a philosophy question than a chemistry question. We're going to use pentane as our solvent. We're going to have left over ammonium chloride and ammonium bromide, because these are not the limiting reagents, so they're definitely going to be there. We're going to have sulfuric acid, because it doesn't get used up in the reaction completely. And we're going to have water, because we're going to add a bunch of water. So now, look, we have pentane and we have water. We have 2 layers. So this is not essentially, but it is a liquid extraction. So we're going to extract the 2 layers. And we're going to have 2 layers, aqueous and organic. So in our organic layer, we're basically going to have all of our organic stuff. So 1-chloro butane, 1-bromo butane, if you want, trace 1-butanol, pentane. So all of our organic stuff, I'm just going to put them like this so I can save space, so I can try to fit this all on the screen, although it looks like I'm going to have to move the camera. The other thing you're going to have is trace sulfuric acid. Sulfuric acid is a covalent compound, so it will somewhat dissolve in pentane. Not a lot, but not zero. And you're also going to have trace water, because anytime you do a liquid-liquid extraction, you get a little bit of water in your organic layer. What about in the aqueous layer? Well, in the aqueous layer, you're going to have your ionic compounds. Your ammonium chloride, your ammonium bromide, your sulfuric acid. Most of it will be in the aqueous layer, and your water. So we've removed a lot of the stuff we want to remove, but we got to get rid of this trace sulfuric acid and this trace water. If you shoot trace sulfuric acid into the GC, it's a big problem. Okay, trace water is not ideal, but it's not as bad as trace sulfuric acid. So we got to get rid of these things. Before we get rid of these things, I can tell I need more space, so I'm going to move the camera and I'll be right back. All right, so now, next, we're going to try to get rid of this trace sulfuric acid. And how we're going to do that is we're going to add saturated sodium bicarbonate, NaHCO3, baking soda. Okay, so we're going to add saturated sodium bicarbonate. It's saturated with water, so this is another aqueous solvent. This is going to react with the sulfuric acid to form sodium sulfate. Sodium sulfate is ionic and completely insoluble in the organic layer. I'm going to link in the description below a video on liquid-liquid extraction that explains this in much greater detail if you're interested in it. This is something we put on lots of quizzes and exams, so it is a good idea to be familiar with this. Okay. Also, we do it like every week, so you're going to get more familiar with it by seeing it more as well. All right. So we're going to end up with the aqueous layer, which is sodium sulfate. No more sulfuric acid, as well as water. And you could argue there's sodium bicarbonate there. You can write that or not write that as far as I'm concerned, because it's obviously there, because you had saturated sodium bicarbonate, you're not going to react all of it. On the organic side, you're going to end up with your 1-chloro-butane, your 1-bromo-butane, your trace 1-butanol, and your trace water. So notice that the purpose of this step was getting rid of the traces of sulfuric acid. It's important to remember from a safety standpoint, this is super, super important. If you add saturated sodium bicarbonate to this mixture, you're going to have problems, because a separatory funnel is a closed system. When you add sodium bicarbonate to sulfuric acid, you get carbon dioxide. So you need to get rid of most of that sulfuric acid in the first extraction step. If you add this to this, the separatory funnel lid can pop off and the entire separatory funnel can actually explode. I've seen that happen before. So it's really, really important that you do this only after you've gotten rid of the sulfuric acid. Furthermore, when you do add this saturated sodium bicarbonate, you want to gently move the separatory funnel and see if a lot of carbon dioxide bubbles are being generated. If they are, you need to be extremely careful and rethink whether you did this step properly. Then make a judgment call, maybe ask the TA if you need to, of whether you should continue or re-extract with water before adding the sodium bicarbonate. Now, I'm not saying you're going to see no bubbles when you add this, but if you see vigorous bubbling, you need to be careful and get the top off that thing so that the carbon dioxide can just go out into the air. It's not dangerous if it's not a closed container, with this possible exception that it splashes out. So use your judgment and be careful when you're doing this. All right, now how do we get rid of the trace water? This one, if you took the course recently, you're very familiar with. We use anhydrous Na2SO4, anhydrous sodium sulfate. We end up with a solid of Na2SO4 and some number of water molecules, and we end up with an organic, which has everything else. 1-chloro-butane, 1-bromo, butane, and maybe traces of 1-butanol. From my experience, we don't actually see 1-butanol on the GC, so we do end up actually getting rid of all of it. But the trace 1-butanol, your call, either include it or don't include it, but be consistent. Final note about this, we don't actually experimentally separate these things. This is now the mixture that we do the GC on. Okay, so there would be pentane in here, which I have somehow lost. Yeah, I lost it in this step. So I forgot pentane here. Good going. And I forgot pentane here. So there will be pentane in here. And so basically we are going to then run the GC on this. And I talked earlier in the video about what that GC is looking like. So I am not going to talk about it again. Finally, for the hypothesis says write one hypothesis for the SN1 reaction and one for the hypothesis for the SN2 reaction. Focus on the ratio between the desired products for each reaction and why the ratio of the products occurred. Include characterization techniques and avoid summarizing the procedure. So if you go back in this video, we talk about this quite extensively. But as a brief review, okay, the SN2 reaction, the 1-butanol, the rate includes the strength of the nucleophile, which leads us to getting less of the chloro product and more of the bromo product, because the bromide, I guess, is a better nucleophile and aqueous acidic media. We're going to analyze this by GC, and we should expect to see a smaller peak for the chloro product and a larger peak for the bromo product. In the case of the SN1 reaction, the rate does not depend on the strength of the nucleophile. So if we start with a 1-to-1 mixture of chloride and bromide, we should end up with a 1-to-1 mixture of the chloro and the bromo products, because the carbocation intermediate can statistically hit the bromide 50% of the time and chloride 50% of the time, because they're a 1-to-1 mixture. In the GC, which is how we're going to analyze this, we expect to see the same peak area for the chloro and the bromo product. One final note I want to give, especially for chemistry majors. You are not allowed to directly compare peak areas of different compounds. You would need to make a calibration curve of this and a calibration curve of this, and then figure out the concentration of this and the concentration of this in solution. However, this is not an analytical chemistry course, so we're not going to be doing that. So we're just going to, they're similar enough molecules that this is okay, but it's not technically a correct thing to do. So just be aware of that. Again, if you're not a chemistry major, that may never come up again. So that is basically everything I've got. I hope you enjoyed the video, and I thank you for watching.